So looking at some questions that we might have with what we just learned. So let's suppose that we have a particular emission spectrum that we're showing right here. And the question is, what element produced this emission spectrum? And we all have four different possibilities for this particular question. It could be hydrogen, it could be helium, it could be beryllium, it could be lithium. And I've shown down here what their particular emission spectra are for those elements. And we want to identify this unknown as to which element it is. So a few things we want to do. Remember we said that each element has its own unique emission spectrum. And so by looking at what particular colors are in our unknown spectrum and trying to match those up with ones for the given elements that we have down here, we can figure out which element it is. Now, on one like this, where the emission spectra are all sort of in the same format, it's pretty easy to look at them and say which one is it, just by just top of your head looking at it here. In this case, you could probably look at this and you can see that this is lithium, just by looking that they match up. But let's try to look a little more in detail at this to make sure that we know how to do this for a case where it's not as obvious. So the first thing to remember is that each set of colors, each set of frequencies, or in this case it's showing it by wavelength, which is perfectly okay because we're treating it like light, which always travels at the same speed if it's in a vacuum. So we'll look at the particular wavelengths here, and we try to match up the wavelengths with the wavelengths that are on these down here. So let's take a look. So let's first look at some very notable lines here. I want to look at this particular line right here. It's sort of an orange, or maybe a yellow. I'd say it's an orange line. And it looks like that it's at a wavelength between 6,000 and 6,500 angstroms. And so I'd say that's maybe about 6,100 angstroms. And so let's see if that line shows up on any of the other element spectra. So let's look at hydrogen first. So hydrogen, we look at about 6,100. There is no line there. So that means this is almost certainly not going to be hydrogen. We'll talk about why that it possibly could be on a later one. We get to some more difficult ones. But right now I'd say that's going to probably knock out hydrogen right there. Then let's look at helium. Does helium have a line at about that 6,100? When we look at helium, 6,100, is there a line right there? Nope, there is no line there either, so it's probably not going to be helium. Lithium has a line about the 6,100, and so that means lithium's a possible candidate. But then we look at beryllium. Beryllium doesn't have a line right. It has a line, it looks like there's a line close to it. If we knew the exact number, we could really tell. But just by that, we say it's probably not going to be beryllium either, because it doesn't really look like there's a line right at that 6,100 bar right here. So we'd say it's almost certainly going to be lithium just by that one. But we can look at other things. We can try going the other way. Looking at, say, hydrogen has a purple line right down here that's like maybe at 4,100. And you can see that there's no line there on this. So that also tells you it's probably not hydrogen. Helium has, let's see, looking at that, helium has a line like a little above 7,000, like 71 or 70, yeah, about 7,100. It happens to be all ones here. And if you look at this, our particular unknown sample doesn't have a line right there, so it's definitely not going to be helium. Lithium, on the other hand, every single line, of course, looks like it matches up. You can see like these four lines right here are also those four lines that are right below 5,500 angstroms. Looking at beryllium, which has the most lines of anything, we can see it has this little cluster of blue lines right about 4,500, a little above 4,500, and our sample one does not have that cluster. And so just by looking at all those different factors, what lines are in this one that are not in these, and what lines are in these that are not in our sample one, we can try to match them up and figure out which one it is. And in this case, that's very clearly going to be lithium based on the information that we have here. So let's try an absorption spectrum. So here's the question. What element produced the following absorption spectrum? So this is now the one that we want to try and figure out. This is going to be a little harder because while the other ones were emission spectra, now we've got an absorption spectrum. So we want to try to identify which element this is. Now, number two, the second thing we're going to have to look at here is the fact that the units are a little different. This one's measured in nanometers, while these are all in angstroms. So we can't even really directly go this between. You can't say, hey, that this line right here is like right here is at like 710 nanometers. Well, there is no 710 nanometers in the other ones. Now, we can do that by doing a conversion, because we could say, well, how many angstroms are in a nanometer, or vice versa. Like, let's say that we have 1 nanometer. Oops, that should be 1 nanometer, not 1 millimeter. So 1 nanometer right here. And we can do a little conversion by saying we want to go from nanometers to angstroms. And if you look at the information that we have, we see that nanometers can go to meters, and then we can go meters to angstroms. So nanometers is 1, nano is 10 to the negative 9th, and then that's going to cancel nanometers down here. Meters on the bottom, angstroms on the top. It's the A with a little circle on top right there. And if you look at what you've got, it says that 10 to the negative 10th meters is 1 angstrom. So 10 to the negative 10th meters is 1 angstrom. That cancels meters. Then we do 1 times 10 to the negative 9th times 1 divided by 1 divided by 10 to the negative 10th. And if you do that math, you get right at 10. So 1 angstrom is, or 1 nanometer is 10 angstroms. So 400 nanometers would be 4,000 angstroms. And so that 400 right there is the same spot as this 4,000 right there. And this 700 right here is the same spot as the 7,000 right here. So that's going to make this pretty easy to compare them. So, but still, we got a little different type of spectrum. How do we figure this out? We're going to do the same thing we did before. Look at individual lines, see which ones match up. For our absorption spectrum here, the one that stands out is this spot right here. Because of the fact that different jumps, different transitions from energy levels are somewhat more common than others, some lines are going to be brighter than others, both on the brighter if it's an emission spectrum or darker if it's an absorption spectrum. And on this particular one, you can see that this line right here is extremely dark, whereas there are other lines, like say this one right here, that aren't nearly as dark. That would indicate that this transition, this energy level transition, is far more common. Now, because there are some that tend to show up and some that are dimmer and you can't see as easily, it may be that some of the lines that we're seeing on this one, especially the dimmer lines, may not show up on here. So we want to try to focus on the bright lines and on the darkest lines. So if it's darkest if it's an absorption spectrum, brightest if it's an emission spectrum. So let's take a look at this spot right here because it looks like it's the brightest line. So that right there is about, looks like about 590 nanometers. And so remember that would be 5,900 angstroms. So let's look and see if there's a 5,900 angstrom line on any of our 4 elements. So 5,900 would be about right here. No line on hydrogen. It means it's probably not going to be hydrogen because that's our brightest line. If anyone shows up here, it should be that yellow one. And so what about helium? Helium, there is a line that's pretty close there. I don't know if it's exactly the same spot, but it looks pretty close. So helium's a possibility. We'll leave helium open here. Lithium, does it have one about 5,900? Nope, nothing about 5,900. So lithium's probably not going to be okay. Beryllium, look at 5,900. Aha, there is one that's about there. So we've been able to narrow this down to say this is probably going to be either helium or beryllium. So let's look for some other ones. The other way we can do this is look for lines that show up on the sample ones, the ones we know, and see if those match up with lines up here. Now, looking at this, we can see very clearly that on both helium and beryllium, there are many more lines than there are on our unknown here. And when that happens, that means you're probably going to have to do more than we did in the first case. Look at individual lines on your original one, and then go down to the other one and see if they match up. But here, let's see if we can find any unique lines here. I'm going to say, look at these right here. There's some green lines that are there. Let's see, are there any green lines about that? Nope, there are green lines down here as well. We don't want to use those green lines because they show up on both helium and beryllium. So do we see any lines that show up on one but not the other? Well, looks like there is a line right about 5,500 right here on beryllium, and there's no line on 5,500 on helium. So let's look and see if that shows up, because if that line shows up, we know it's probably beryllium, and if it doesn't show up, it means it's more likely to be helium. So about 5,500. So 5,500 would be 550 nanometers, so that's right in the middle here. No lines. Nothing in here at all. But for beryllium, there are a bunch of lines all in there. And so while it's not 100% guaranteed this is going to be helium, that means that if I had to choose between these two, I'd say this is probably more likely to be helium than other ones. And if you look at it, you can sort of see those as well here, because there's a line right above 7,000, there's a line right above 700 nanometers. There's a line about 6,700, which would be 670. There's a line right about 670 right here. So helium seems to match up pretty well. But notice that it doesn't match up perfectly. Helium has a 4,000 line, which is about 400. I don't see one here. But this is a really dim line. Because of the fact that's not a very dim, not a very bright line, it may just be that whatever piece of equipment we used to measure this just wasn't sensitive enough to see it, because that's a much more uncommon energy level transition. So looking at the preponderance of the evidence we have here, Our best guess on this is that this is going to be helium, and it's not going to be beryllium. And so that would be how you use an absorption spectrum and how you analyze that using your emission and absorption spectrum. So in this case, we say an element was measured in a spectrophotometer, and that measures what wavelengths of light are absorbed. And the question is, what element is it? And so over here, we have our graph from our spectrophotometer. And so what it shows is it shows the wavelength in nanometers on our x-axis. It shows the intensity, the brightness of how much, or in this case, the opposite brightness, how much of that wavelength of light was absorbed. And so this doesn't look like a spectrum we saw before. This is actually a version of an absorption spectrum, but we can use it the same way. Because notice that there are several different peaks that are on this. There's a peak right here, really tall peak. That's our brightest line, or our most important transition. It looks like it's somewhere about, see, there's 600s here, 800s here, so 700s right there. So it looks like to be maybe about 650-ish. There's another line that's right here. That one looks to be, so there's 400, 600, 500s here, so maybe 490. So just for right now, just to keep things straight, I'm going to write some of these down up here so I don't know exactly where they are. This gives me an idea. So we said that this first one is probably maybe 650 to maybe 660 nanometers. Right there is where that line is. This line right here is looking like it's probably about 490-ish nanometers. We have like a few really tiny lines down here. There's this one right here, which is probably maybe 450. And there's another little one that's right there that's maybe 415 or so, maybe 420 or maybe 415. And there may even be a little one that's down below. It's really, really hard to see that might be even right at about 400. It's really hard to see. So that one's sort of maybe a question mark because we're not quite certain we can see that on here. But we have a few lines that we can look for. So let's see if these show up. The brightest line is the one that's 650 to 660. So let's look for that one first. So these are in nanometers. Remember, these are angstroms. But we knew that 1 nanometer equals 1 angstrom. So we're just going to take the numbers up here and multiply them by 10. That'll give us the amount in angstroms. So 650 to 660 would be 6,500 to 6,600. Let's look at hydrogen. Is there a line about 6,500 to 6,600? Yes, hydrogen does have a line that's right here, so hydrogen is a possibility. Helium, does it have a line that's in that range? Okay, helium does as well. There's one that's right about in that range as well, so it could also be helium. Let's look at lithium. Does lithium have a line that's about 650 to 660? Maybe. There's a line right here. It's a little farther north than we'd expect, a little higher than we'd expect it to. I don't think that's enough to throw it out, though, so we're going to have to leave that by itself. And then let's look at beryllium. Beryllium also has lines right about in there, so that could be it right there. So our first line doesn't really tell us anything, at least for the samples that we have right here. Our next line is 490 nanometers, and so that'd be 4,900 angstroms. So let's look and see if that one shows up. 4,900 angstroms, it looks like it does show up on the hydrogen. It looks like it does show up on the helium. 4,900 angstroms. Doesn't show up really on the lithium, because lithium's got one, lithium's got one that's right at about 5,000, but really doesn't have one that's below, it's about 100 below it. It's sort of, because the one we're looking for is sort of right in between these two lines. So, probably not lithium, but we'll keep looking here. Beryllium, does it have anything that's right in that range of about 4,900? Once again, it's sort of got one that's sort of close, but I'd say lithium and beryllium aren't looking so hot. Hydrogen and helium are looking like it's definitely possibilities. So let's look at the next one here. The next brightest one is the one that's about 450 nanometers on our original one. And so that'd be 4,500. So do we have a 4,500 on hydrogen? Hydrogen, doesn't look like it has really one on the 4,500. It has one that's a little below that. Now our 450 could possibly be a 440, so that might be this one right here. That's sort of hard to tell here. Helium's also got one that's right about there, though, so that really doesn't help us much either. It definitely has about a 450. Lithium does not have anything that's in that range, so I think we can cross that lithium. That's 2 no's on that one right here. Beryllium, though, still has some lines that are around in that spot, so beryllium is probably not it, but once again, it's not. We haven't had 2 no's on that one here. And the other two are such small peaks, I'm not certain really we could use those all that well. 415, 400, and so, that could, it's hard, we don't want to really focus on really tiny peaks here. So our next thing to do would be go the other way. Look for things that are in our guys down here and see if they show up on our other one here. So hydrogen really has one, the 6500, the one that's right at about 5,000, and so far those are all on our picture up here. Really hydrogen, other than some of these, that maybe this one, well, that one down there, about 4,100, might fit the 415 that's up here. So hydrogen seems to fit everything. Hydrogen is probably going to be our candidate because everything that's on our hydrogen spectrum also shows up in our spectrometer plot. Let's look for helium. Helium has this nice bright line right at about 5,900. And so this one right here has no line at 1,500. There's no peak there. And so that probably is going to toss out helium as a candidate because helium has a bunch of other things too. It's got these lines at like 7,000 and 75. There's nothing there. That doesn't by itself disqualify it, but it makes it more unlikely. It's got some lines that are above 5,000. There are no lines above 500 here. It's got a bunch of lines down here, and there's got a bunch of them down there. So maybe that could be a possibility. But really, that big, bright yellow line for helium, that's a deal killer right there, because it definitely did not show up on here, and it's definitely a really bright line on this line, which means it's an important one. The other possibility is beryllium. Beryllium has lines all over the place here. And so it's got all sorts of lines way up here, and we don't see any of those on here. It's got a bunch of lines that are between 5,000 and 7,000 in here. And ours should really only have one line, that's 650, 660. But between 5,000 and 7,000, it's got lots and lots of lines. It's definitely another one about the 5,900 place. Then we have nothing there on our other one here. So I think this is almost certainly, based on what we see here, going to be hydrogen. Because almost every single one of hydrogen's lines matches up with a line up here, and all the lines that are up here match up with something on hydrogen, which is not true for the other elements. So that's how we break down one like that. So we've gotten pretty good at being able to identify which element is producing a certain spectrum, a particular absorption or emission spectrum. But we haven't really gone into how we show that this is produced by these electron energy levels. So let's look at that. So we have a hydrogen absorption spectrum up here, and this one nicely actually gives us the actual numbers. It doesn't just have, we don't have to sort of look at it and try to read it. This one tells us our first line here is 410 nanometers. This is nanometers right there. The second one's at 434, 46, and 656. And so that's going to make things a little bit easier here. And over on the right side, we have the energy levels for hydrogen, showing what the different energy levels are, starting with the first energy level, second, third, and so on, and the energies that they have in electron volts. And so we now know the energies, we know the frequencies that are being emitted or absorbed, in this case, by the hydrogen. And the question is, show that the hydrogen spectrum is consistent with the energy level of hydrogen. And so what that means is we want to show that for these frequencies that are listed right here, that for those frequencies, each one corresponds to a particular jump or a particular drop or rise, a particular difference in energy levels of the hydrogen atom. So to do this, we're going to have to go through a couple steps. We're going to start with our wavelength that we have here, the 410 or the 434, the 486 or the 656, and we're going to convert that to a frequency. Because if we can find the frequency of that particular wavelength, we know we can find the energy. Because we learned last time is that we've got this nice little equation that says that energy of electromagnetic radiation is equal to h, the Planck constant, times the frequency. So if we can find the frequency from the data that's here, then we can figure out the energy. And if we know the energy, we can check and see if that energy corresponds to a difference between any two energy levels, whatever those would be. We don't know what they're going to be yet, but we can check and see if it matches up with one of them. So let's start off with one of these right here. So just to start this off, let's pick the 486. And so we'll pick this guy right here, sort of that green line. And so with the 486, we're starting off with 486 nanometers. We don't want nanometers, though. We're going to want this in meters. And the reason why is that our next equation, this is the one we talked about last week as well, is that the relationship between frequency and wavelength for a wave. And that's that the speed of a wave, v, equals f times lambda. The speed of a wave is equal to its frequency times its wavelength. So here, we got the wavelength. We know the speed of light. The speed of any electromagnetic radiation in a vacuum is going to be equal to 3 times 10 to the 8 meters per second. So we have the velocity, we have the wavelength. Since this is in meters per second, this also needs to be in meters. So we're going to start off by converting this. And so we want to go from nanometers to meters. We said 1 nanometer is 10 to the negative 9 meters. And so we do that math right here, and I get 4.86 times 10 to the negative 7th meters. All right, so now we have our distance in meters. We're going to take that, put that into our v equals f lambda so we can figure out the frequency. So v is the speed, so that's the 3 times 10 to the 8, so that's v. And that's going to equal the frequency, which is what we don't know, times our lambda, our wavelength, which we just figured out in meters is 4.86. Oops, I don't want to work here today. 86 times 10 to the negative 7th meters. And that's going to be our lambda because we know that v equals f times lambda right there. All right, so now we just have to solve for f. And so to get f by itself, we'll divide both sides by 4.86 times 10 to the negative 7th, and divided by 4.86 times 10 to the negative 7th. That's going to cancel it over here, and I end up getting a frequency. Let's see, put in the calculator. Comes out as 6.1728 times 10 to the 14th. And that unit, remember, is going to be in hertz. Frequency is going to be about hertz once we use this right. So, okay, we have the frequency now. Now we want to find the energy. Well, we use our E equals HF, so that the energy of this is going to be equal to the H. H is Planck's constant, and so this is one that we talked about last time, that Planck's constant is equal to 6.626 times 10 to the negative 34. It's not one you need to know, but it's one you need to be able to know how to look up whenever you need it. So but you haven't memorized, but you probably have it in your notes somewhere. And on an assessment, that's something I would give you, and you just have to give you that data in somewhere. You'd have to locate it. And then times the frequency, which we said is the 6.1728 times 10 to the 14th power. And so when we do this, we should get an energy in joules. And so we put those in the calculator, and let's see. When I do that, I get 4.0901 times 10 to the negative 19. 0901 times 10 to the negative 19th, and the units there are going to be in joules. Now, the problem is our energies over here are all in electron volts. Now, it tells us here 1 electron volt is equal to this many joules, and so we're going to have to do a little unit conversion here. And so we'll say 4.0901 times 10 to the negative 19th joules. And we're going to go from, we said there are 1.602 times 10 to the negative 19th joules in 1 electron volt. And then whenever I do that, I end up getting 2.5531. So 2.5531 electron volts. All right, so that at least makes some sense here. So this is what we start with. Just looking at our sig figs here, since our original value started off with 486, that's 3 sig figs. We'll round this to 3 sig figs, so that's 2.55 electron volts for purposes of comparison. So what we want to know is, are there any drops or any rises, any changes from one energy level to another energy level that are equal or almost exactly equal within rounding differences to 2.55? So let's look at our differences. So first, let's look at maybe 2 to 1, from second energy level down to first energy level. We go from negative 3.4 down to negative 13.6. Well, that's definitely not 2.55. That's closer to 10. Let's look at our next set here. Let's say we go from third energy level down to second. That would go from 1.51 to 3.4. That's closer, but still that's closer to 2. What if we went from, let's say, negative 0.85, which is the what is that? That's the fourth energy level, down to the 3.4. And so if we do that, let's see, that would be pretty close. So let's actually work out the number on that and see what we get. So we're going to look at going from the fourth energy level down to the second energy level. So that's going to be negative 0.85 minus negative 3.40. And so negative 0.85 minus negative 3.40. And when I do that, it gets out to be 2.55 electron volts. Exactly the same as what we had here. And so this, right here, this particular 486, is the transition of the hydrogen atom from its electron, from its fifth energy level, down to its second energy level. Or in this case, because of the absorption spectrum, it means that whenever this light came in and it hit this atom, it caused an electron to jump from the second up to the fourth. And we know that it's second and fourth is because the difference in energy there is 2.55 electron volts. And if we take 2.55 and we take this 486 right here as a wavelength here, and we calculate the energy of that light, it comes out to be exactly 2.55 electron volts. And so we could do the same thing with any one of these, the 410, the 434, the 656, and we'd find that each one corresponds to a different set of shifts of electrons from one energy level to another.